Algebra 2, Chapter 10, Section 3, Working with the Exponent of an Exponential Expression. Let's start with some examples, and then we're going to make some generalizations. So first, let's think about the value V in dollars of an investment T years after the year 2004. So T is in years after 2004, is given by the following equation. Part A, how much is the investment worth in 2016? 2016 would be how many years since 2004? It would be 12. So T for the first one would be 12. So we would have 4,000 times 2 to the 12th over 12. 12 over 12, of course, is 1. So we'd have 2. So basically double. 4,000 times 2 is 8,000. 2028 is another 12 years later. We would have another factor of 2, which means we would double the previous value, 16,000. And 2040 is another 12 years later after that, so we would double 16,000 to $32,000. That's the answer to part A. Use the form of the expression to explain why the value doubles every 12 years. Well, it doubles every 12 years because every time we put 12 in, we get another factor of 2. So if we think of this, when the exponent goes up by 1, if we were to factor let's put this into a different form. So if we put 2 to the 1/12th to the t, instead of 2 to the t over 12, every time we get t to the t is 12, we end up with just another doubling. Maybe this doesn't really help putting it in this form. Let's just say 2t to the 12 when t is a multiple of 12 will be some power of 2, because we'll have an integer here for t. Use the exponent laws to put this in a form that shows it is an exponential function. That's what I was doing. Sorry, I got ahead of myself. So 4,000 times 2, and then we can just think of t over 12 as 1/12 times t, which would be 4,000 times 2 to the 1/12 to the t. And we can use a calculator to find 2 to the 1/12 power. So if we pull up a calculator, we can find 2 to the 1/12 power is 1.05946. 1.05946 to the t, roughly. And now it's clear this is exponential a. That's a, that's b to the t. Let p of t be 1,000 times the quantity 1/2 the t over 7. It's a population of a town t years after it is founded. What is the initial population? Well, remember the initial population will always be a, because when we put in 0 here, we'll have something to the 0, which gives us 1. 1 times 1,000 is 1,000. So part A, 1,000 is the initial population. After 7 years, we will have 7 over 7 is 1. We'll have half of 1,000. After 14 years, it would have again a 250. And when is the population 125? Well, if we have 250 again, we get to 125, which would be 21 years. So this town is shrinking exponentially. It's decaying. Rewrite p of t in the form p is the p of t is a times b to the t. Give constants a and b, and find the annual growth rate. So again, we take p of t is 1,000, and 1/2 to the 1/7 So splitting the dividing by 7 into a multiply of 1/7, and then using that regrouping exponent to an exponent rule, we can write this expression. So if we use our calculator, we can find 1/2 to the 1/7. So 1/2 is 0.5. And we get 0.90572. 0.90572. Let's check that. 90572 is the correct number to the t. 1,000 times that. So A is 1,000. B is about 0.90572. And remember, you don't want to overround this number because we might want to subtract from 1, which is what we're going to do in a minute. And of course, that's to the t power. So the annual growth rate, this is the growth factor. Remember, B is 1 plus r. So B minus 1 is r. So if we subtract 1 from B, we get r, the rate, which of course will be negative, and it asks for the growth rate, so the answer should be negative. So if we find calculator, we can subtract by 1 and get negative 0.09428. Negative 0.09428, which is rounded the correct way to match that. So our rate would be, as a percent, we could call it negative 9.428% growth. So here's part of our answer. Here's the other part. The number of people owning the latest gadget after t days is given by n of t is 450 times 3 to the t over 6. How many people have the latest gadget in 6 days, 12, and 18 days? So first, in 6 days, we have 450 times 3 to the 6 over 6, which is 1, which again is just 3. So 450 times 3, that would be 900, 1350. So that's 1,350 people after 6 days. After 12 days, we have 3 to the 12 over 6, which is 2, or 3 squared, which is another tripling. So it would be triple this number, which would be so it would be 4,050, if I did the math right. Because we have I think it's 4,150. Let's check with the calculator. So 1,350 doubled, or 450 not doubled, tripled. So it started with 450, tripled was 1,350. Triple that is 4,050. I was right the first time. Don't doubt yourself too much. And now triple it again for 18 days. 18 over 6 is 3. So triple 4,050 will give us 12,150, which we can check with the calculator. Triple it again. 12,150. So you can see now we're tripling every 6 days when this factor is a 3. So we can generalize what we've just seen. The first quantity doubled every 12 months, and our number that was a base was 2, and then we have the period of time it's doubling over here divided by t divided by that number. Here we halved every 7 years, and then we just saw tripling every 6 days. So in general, the quantity Q is A, and this B is different than this is not the annual growth rate, or the annual growth factor, I mean. But we still use B here, which is confusing. So it's a different B. We could call this something else, but it's still a base, so we use B. A, B to the t over t grows by a factor of B every t units of time. And this is just a scaling of the input. So you could think of it that way to help you remember. We're dividing the input by t to scale it up by t units of time. So now we can write directly if someone says, you know, my bank account doubles every 10 years. We can just write my initial balance, whatever it happens to be, Q naught for quantity. So it's doubling, so we put a 2 for doubles every 10 years, T over 10. And then we can find, if we wanted to know the annual growth rate, we could find that by just taking 2 to the 1/10. 2 to the 1/10 and subtracting 1, 7.177% is the annual growth rate. Okay, so remember, rate is plus 1 is the growth factor. So we can use this information to analyze certain kinds of investments. Which is better, an account that earns 1% per month or earning 12% per year? And here we're going to be converting between different time scales. So that's the theme of this problem. So an investment that earns 1% per month after a year, so after 1 year, the one that earns 1% per month will have gotten its monthly factor 12 times. So we'd have accumulated 12 months of growth. So if you think of the quantity, it would be the initial quantity times 1.01, because we add 1 from the percent. So 1% is 0.01. That's the rate. We add 1 to get the growth factor. 1.01 to the m, where m is the number of months. So after a year, our quantity would be the initial quantity times 1.01 to the 12th. That's for the account that earns 1% per month. For 12% per year, it would just be a simple 12% for the whole year, because you just have 1 in the exponent. So 1.01 to the 12th power, multiplying 1.01 by itself 12 times, is 1.1268 times the initial quantity. So we get more money in our account if it's 1% per month. We actually have a 12.68% instead of 12%. So we get an extra 0.68% of growth for that year. So it's 1% per month is better. This is also another example relevant to time scale. The population in thousands of a town after t years is given by p equals 50 times 1.035 to the t power. What is the annual growth rate? So we just need to subtract 1 from b to get 3.5% growth. Write an expression that gives the population after m months. Okay, so this was in years. So if we think about this, we can write a little equation for part B. The number of months, if we have the number of years, we can write an equation. The number of months would be 12 times the number of years, because after 1 year we have 12 months. After 2 years it would be 24 months, and so on. We can solve this for t. So if we solve this for t, we get t is equal to m over 12, dividing both sides of the equation by 12. And now we can substitute in this equation t. So we could say p is 50 times 1.035 to the m over 12. And this should look similar to what we were just talking about, where we're dividing by the number of units of time that we apply that growth factor to. So use the expression in part B to find the town's monthly growth rate. So here's our expression. So for C, we just need to find the monthly growth rate. So we have 1.035 is our yearly rate, or yearly factor. 3.5% is the yearly rate to the 1/12 to the m times 50 is equivalent to this expression. And this is kind of our monthly factor. So our monthly factor would be 1.035 to the 1/12. So pulling up a calculator, 1.035 to the 1/12th power is 1.00287, and don't overround. 1.00287. Writing a 3 here is way over rounding, because you'll see now we need to find the rate. We subtract off this 1, and we're left with 0.287% as our monthly growth rate. Monthly growth rate is 0.287%. And remember, we subtract 1 to find the rate. For percent, we move over twice. We still have the decimal here to the left of the 2. Be careful. So that was showing us how we might scale the time. Here we're going to shift the exponent. So the population of a town was 1,500 people in 2005, increasing at a rate of 2.5% per year. Express the population in terms of the calendar year y. So this would, y would be 2005 here when we have 1,500 people. So how can we do that? Well, we can simply shift the input. So if we had 1,500 people, we could say our rate per year is 2.5, so our annual growth factor is 1.025, adding 1 to this. Per year, t, but we can shift t to be the calendar year by subtracting the input year from the original year. So we're just shifting, essentially shifting the graph right by 2005 is one way of thinking of this, or shifting the input of our function. Why 2005? Because we want 2000, when we put 2005 in, we want this to be 0, so there's no growth, and we get 1,500 out. Okay, so a population is this, and that's the answer to the first part of the question. We're not done though, that's just this part expressed. Now what is the town's population in 2014? We just need to plug in 2014 for y and subtract 2005, and we get 2014 minus 2005. We could do that in our head. The answer is 9, but might as well use our calculator to make sure we don't make a silly mistake. Okay, so we have 9, 1,500. I say silly, really, I just mean like a simple mistake, an arithmetic mistake. It's good to double check our arithmetic when we can. So 1.025 to the 9th times 1,500 to the 9th times 1,500 is 1,873. And when you're answering a word problem in people, there's no reason to round below the whole number of people. So we'll just write 1,873 is the approximate population in 2014.